Optical communication, also known as optical telecommunication, is communication at a distance using light to carry information. It can be performed visually or by using electronic devices. The earliest basic forms of optical communication date back several millennia, while the earliest electrical device created to do so was the photophone invented in 1880s. Light. Light is a type of electromagnetic radiation like radio waves. It is a wave of oscillating electric and magnetic fields propagating through space. Its frequency, falling between microwaves and X-rays, is extremely high that it can accommodate very high rates of data, making it extra reliable for transmission. The optical spectrum is made up of infrared, visible, and ultraviolet light. Today, infrared light is being used increasingly as the carrier for information in communication systems. Light waves are very short and are usually expressed in nanometers or micrometers. Actually, visible light is in the 400 to 700 nanometer range. Light waves travel in a straight line as microwaves do. Its speed depends upon the medium through which the light passes. However, it is approximately 300 million meter per second or about 186,000 miles per second in vacuum. The unit of measure for light wavelength is the angstrom. 1 angstrom is equal to 10 to the negative 10 meter. Light can be processed or manipulated in many ways, and these ways are called physical optics. The simplest way of manipulating light is to reflect it. When light rays strike a reflective surface such as a mirror, the light waves are thrown back or reflected. If the light ray strikes the mirror at some angle A from the normal, the reflected light ray will leave the mirror at the same angle B to the normal. This principle is known as the law of reflection. This is usually expressed in the following form. The angle of incidence is equal to the angle of reflection. The light ray from the light source is usually called incident ray. The direction of the light ray can also be changed by refraction, which is the bending of a light ray that occurs when the light rays pass from one medium to another. Unlike with reflection, wherein the light ray bounces away from the reflecting surface, in refraction, the light rays are being absorbed by or passes through transparent materials such as air, water, and glass. Refraction also takes place at the point where two different substances come together. For example, when air and water come together, refraction occurs, and the dividing line between them is known as the boundary or interface. Also, refraction occurs because light travels at different speeds in different materials. The amount of refraction of the light of a material is usually expressed in terms of the index of refraction. This is the ratio of the speed of light in air to the speed of light in the substance. It is also a function of the light wavelength. The difference of reflection with refraction is seen in this figure. We can see that the light ray that bounces the surface is the reflected ray, and the one that passed through the surface is the refracted ray. Optical communication systems use light to transmit information from one place to another. It uses a transmitter which encodes a message into an optical signal, a channel which carries the signal to its destination, and a receiver which reproduces the message from the received optical signal. The transmission medium is either free space or a light-carrying cable called a fiber optic cable. Both media are used, although the fiber optic cable is far more practical and more widely used. The main limitation of communication systems is their restricted information carrying capabilities. This means that the communication medium can carry just so many messages. This information handling ability is directly proportional to the bandwidth of the communication channel. Using light as the transmission medium provides vastly increased bandwidth. The figure shows the elements of an optical communication system using free space. It consists of a light source, modulated by the signal to be transmitted, a photodetector to pick up the light and convert it back into an electric signal, an amplifier, and a demodulator to recover the original information signal. Light source is an optical transmitter that is paired with an optical receiver, both of which are connected to electrically based devices or systems. Common light sources are light-emitting diodes, or LEDs, and lasers. A transmitter is also a light source. These sources can follow electric signal changes as fast as 10 GHz or more. Lasers generate monochromatic or single-frequency light that is fully coherent, meaning all the light waves are lined up in sync with one another and as a result produce a very narrow and intense light beam. A modulator is used to vary the intensity of the light beam in accordance with the modulating baseband signal. Amplitude modulation, also referred to as intensity modulation, is used where the information or intelligent signal controls the brightness of the light. Analog signals vary the brightness continuously over a specified range. This technique is used in some cable TV systems. A modulator for analog signals can be a power transistor in series with a light source in its DC power supply, as shown in the figure. Pulse modulation refers to turning the light off and on in accordance with some serial binary signal. The most common type of pulse modulation is pulse code modulation, which is serial binary data organized into bytes or longer words. A photodetector acts as the receiver, as it picks up the modulated light wave being transmitted. This is usually a photodiode or transistor whose conduction is varied by the light. The small signal is amplified and then demodulated to recover the originally transmitted signal. Light beam communication has become far more practical with the invention of the laser. It produces a very narrow beam of brilliant light of a specific wavelength. Because of its great intensity, a laser beam can penetrate atmospheric obstacles better than other types of light can, thereby making light beam communication more reliable over longer distances. Today, fiber optic cables have been highly refined that cables many miles long can be constructed and then interconnected for the purpose of transmitting information. Also, a great advantage of a fiber optic cable is its immense information carrying capacity, meaning it has a wide bandwidth. Shown in the figure are the components of a typical fiber optic communication system. The information signal to be transmitted may be voice, video, or computer data. First, the information signal enters the decoder or converter to convert the information to a form compatible with the communication medium, usually converting continuous analog signals to a series of digital pulses. These digital pulses are then used to flash a powerful light source off and on very rapidly. Then the light beam pulses are fed into a fiber optic cable which can transmit them over long distances. At the receiving end, a light-sensitive device known as a photocell or light detector is used to detect the light pulses. It converts the light pulses to an electric signal. The electrical pulses are then amplified and reshaped back into digital form and are fed to a decoder, where the original video or voice is recovered. Fiber optic communication systems are being used more and more each day. Their primary use is in long-distance telephone systems and cables TV systems. Fiber optic networks also form the core or backbone of the Internet. Other applications of the fiber optic communication systems are the following: interconnecting computers in networks within the large building, carrying control signals in airplanes, ships, and in TVs, etc. As I have said earlier, the main benefit of fiber optic cables is their enormous information carrying capability. Other benefits of fiber optic cables over conventional electrical cables are the following: wider bandwidth, low loss, lightweight, small size, security, interference immunity, and greater safety. A fiber optic cable is thin glass or plastic cable that acts as a light pipe. It is not really a hollow tube carrying light, but a long, thin strand of glass or plastic fiber. Some fiber optic cables are the same size of a human hair. A light source is placed at the end of the fiber, and light passes through it and exits at the other end of the cable. Fiber optic cables come in a variety of sizes, shapes, and types, from a cable that contains a single strand of fiber to a complex one with multiple fibers with different layers and other elements. The portion of a fiber optic cable that carries the light is made from either glass, sometimes called silica, or plastic. The fiber, which is called the core, is usually surrounded by a protective cladding. This cladding is also made of glass or plastic but has lower index of refraction, ensuring that the proper interface is achieved so that the light waves remain within the core. Typically, the division between the core and the cladding cannot be seen because they are usually made of the same type of material. Over the cladding is usually a plastic jacket similar to the outer insulation of an electric cable. There are two basic ways of classifying fiber optic cables. The first method is by the index of refraction, which varies across the cross-section of the cable. The second method is by mode, which refers to the various paths the light rays can take in, passing through the fiber. The two ways to define the index of refraction variation across a cable are the step index and the graded index. Step index refers to the fact that there is a sharply defined step in the index of refraction where the fiber core and cladding interface. It means that the core has one constant index of refraction and the cladding has another constant index of refraction. When the two come together, there is a distinct step. The other type of cable has a graded index. Here, the index of refraction of the core is not constant. Instead, it varies smoothly and continuously over the diameter of the core. The closer the center of the core, the higher index of refraction, obtaining a peak at the center of the core and then declining as the other outer edge of the core is reached. The index of refraction in the cladding for this type is then constant. Mode refers to the number of paths for light rays in the cable. There are two classifications, single mode and multi-mode. In single mode, light follows a single path through the core, while in multi-mode, the light takes many paths. In practice, there are three commonly used types of fiber optic cable: multi-mode step index, single mode step index, and multi-mode graded index. The multi-mode step index fiber cable is probably the most common and widely used type. It is also the easiest to make and therefore the least expensive. It is widely used for short to medium distances at relatively low pulse frequencies. The main advantage of a multi-mode step index fiber is its large size. Large diameter cores are excellent at gathering light and transmitting it efficiently. The problem with this is that it stretches the light pulses. This stretching of the pulse is referred to as modal dispersion. A single mode or monomode step index fiber cable essentially eliminates modal dispersion by making the core so small that the total number of modes or paths through the core is minimized. Typical core sizes are 2 to 15 micrometer. With minimum refraction, little pulse stretching occurs. Single-mode stepped index fibers are by far the best since the pulse repetition rate can be high and the maximum amount of information can be carried. This type of cable is highly preferred in very long-distance transmission and maximum information content. Although the problem with this is that it is extremely small, difficult to make, very expensive, and also difficult to handle. Multi-mode graded index fiber cables have several modes or paths of transmission through the cable, but they are much more orderly and predictable. As a result, this cable can be used at very high pulse rates, and therefore a considerable amount of information can be carried. And because this cable is much wider in diameter, it is easier to splice and interconnect, and is cheaper, less intense light sources can be used. Fiber optic cable specifications. The most important specification of a fiber optic cable are size, attenuation, and bandwidth. Fiber optic cable comes in a variety of sizes and configurations. Size is normally specified as the diameter of the core over cladding. Common sizes for single-mode fibers are 9 over 125 or 8.3 over 125, while 50 over 125 or 62.5 over 125 in multi-mode fiber. The dividend represents the diameter of the core, while the divisor as the diameter of the cladding, both in micrometers. Cables come in two common varieties, simplex and duplex. Simplex cables, as the name implies, is just a single fiber core cable. On the other hand, in duplex cable, two cables are combined within a single outer cladding. The most important specification of a fiber optic cable is its attenuation. Attenuation refers to the loss of light energy as the light pulse travels from one end of the cable to the other. The light intensity of the light at the output is lower than that on the input because of various losses in the cable. The main reason for the loss in light intensity over the length of the cable are light absorption, scattering, and dispersion. The bandwidth of a fiber optic determines the maximum speed of the data pulses the cable can handle. Bandwidths are normally stated in megahertz kilometers. As the length of the cable is increased, the bandwidth decreases in proportion. When long fiber optic cables are needed, two or more cables can be spliced together, as the splicing fiber optic cable means permanently attaching the end of one cable to another. The first step is to cut the cable, called cleaving the cable, so that it perfectly fits on the end. The two cables to be spliced are then permanently bonded together by heating them instantaneously to high temperatures so that they fuse or melt together. Special tools and machines must be used in cleaving and splicing to ensure clean cuts and perfect alignment. Meanwhile, connectors are special mechanical assemblies that allow fiber optic cables to be connected to one another. They ensure precise alignment of the cables.
Optical transmitters and receivers. In an optical communication system, transmission begins with the transmitter, which consists of a carrier, generator, and a modulator. The carrier is a light beam that is modulated by turning it on and off with digital pulses. The basic transmitter is essentially a light source, and the receiver is a light or photodetector that converts the received light back into an electrical signal. To transmit high-speed digital pulses, a very fast light source must be used. The two most commonly used light sources are light-emitting diodes and semiconductor lasers. A light-emitting diode, or LED, is a p-n junction semiconductor device that emits light when forward biased. Because an LED is a fast semiconductor device that can be turned off and on very quickly and is capable of transmitting the narrow light pulses required in a digital fiber optic system. The other commonly used light transmitter is a laser, which is a light source that emits coherent monochromatic light. Coherent refers to the fact that all the light waves emitted are in phase with one another, and monochromatic light is a pure single frequency light. The most widely used light source in fiber optic systems is the injection laser diode, also known as Fabry-Perot laser. An LED light transmitter consists of the LED and its associated driving circuitry. Most LED light transmitters are used for short distances, low speed, digital fiber optic systems. Further, the speed of the LED is limited. Turn off and turn on times are no faster than tens of nanoseconds, and so transmission rates are limited. Most of the circuitry is contained in a single integrated circuit. This circuit can operate at a data rates up to 3.125 Gbps. A multiplexer either passes the input data directly to the laser driver transistors or selects data that is clocked via a flip-flop in an external differential clock signal. Enable or disable signals turn the laser off or on. The laser diode is connected to the driver by means of several resistors and a capacitor that set the current and switching response. Most laser packages also contain a photodiode that is used to monitor the laser light output and provide feedback to the APC circuit in the chip. The receiver part of the optical communication system is relatively simple. It consists of a detector that senses the light pulses and converts them into an electrical signal. This signal is amplified and shaped into the original serial digital data. The most critical component is the light sensor. The most widely used light sensor is the photodiode. It is a silicon PN junction diode that is sensitive to light. This diode is normally reverse biased. The phototransistor amplifies the small leakage current into a larger, more useful output. Phototransistor circuits are far more sensitive to small light levels, but they are relatively slow. Thus, further amplification and pulse shaping are normally used. PN diodes are more sensitive than the PN junction photodiode. PN diodes are also significantly faster in response to rapid light pulses of high frequency. The avalanche photodiode is widely used and is the fastest and most sensitive photodiode, but it is expensive and its circuitry is complex. Like the standard photodiode, the APD is reverse bias. The APD uses the reverse breakdown mode of operation that is commonly found in Zener diodes. The high reverse current requires less amplification than the small current in a standard photodiode. Optical transceivers or transponders are assemblies called optical modules into which both the light transmitter and light receiver are packaged to form a single module. These modules form the interface between the optical transmission medium and the electrical interface to the computer or other networking equipment. These modules are made up of the transmit optical subassembly and the received optical subassembly. A power budget, sometimes called a flux budget, is an accounting of all the attenuation in gains in a fiber optic system. Gains must be greater than losses for the system to work. The following are the numerous sources of losses in a fiber optic cable. Cable losses, connection between cable and light source, and photodetector, connectors, splices, cable bend. There are several ways to overcome the attenuation experienced by a signal as it travels over fiber optic cable. Number 1. Use newer types of cable that inherently have lower losses and fewer dispersion effects. Number 2. Use regeneration. Regeneration is the process of converting the weak optical signal to its electrical equivalent, then amplifying and reshaping it electronically and retransmitting it to another laser. This process is generally known as optical electrical optical conversion. Number 3. Use an optical amplifier. Optical amplifiers boost signal level without OEO conversion. Wavelength division multiplexing. Data is the most easily multiplexed on fiber optic cable by using time division multiplexing. However, developments in optical components make it possible to use frequency division multiplexing on fiber optic cable, which permits multiple channels of data to operate over the cable's light wave bandwidth. Wavelength division multiplexing, another name for frequency division multiplexing, has been widely used in radio, TV, and telephone systems. The first coarse WDM systems used two channels, operating on 1310 and 1550 nm. Later, four channels of data were multiplexed. Dense wavelength division multiplexing refers to the use of 8, 16, 32, 64, or more data channels on a single fiber. Current DWDM systems allow more than 160 individual data channels to be carried simultaneously on a single fiber at data rates up to 40 Gbps, giving an overall capacity of 160 by 40 or 6400 Gbps. Arrayed waveguide grating is an array of optical waveguides of different lengths made with silica on a silicon chip that can be used both multiplexing and demultiplexing. AWGs are popular because they are relatively easy to produce with similar semiconductor processes, making them very expensive. Passive optical networks. The primary applications for fiber optic networks are in wide area networks, such as long distance telephone service and the internet backbone. As the speeds have increased and prices have declined, fiber optic technology had been adopted into MANs, storage area networks, and LANs. The most widely used of these technologies are the following: SONET, Ethernet, and Fiber Channel. A newer and growing fiber optic system is the passive optical network, a type of MAN technology. This technology is also referred to as fiber to the home. Similar terms are fiber to the premises or fiber to the curb, designated as FTTP or FTTC. Most optical networking uses active components to perform optical to electrical and electrical to optical conversions during transmission and reception. This is an expensive and a problematic structure. One solution to this problem is to use a passive optical network. The term passive implies no OEO repeaters, amplifiers, or any other device that uses power. In an PON, the transmitter sends the signal out over the network cable, and a receiver at the destination picks it up. There are no intervening repeaters or amplifiers. Only passive optical devices such as splitters and combiners are used. By using low attenuation fiber optic cable, powerful lasers, and sensitive receivers, it is possible to achieve distances of up to about 20 km without intervening active equipment. The figure shows a passive optical network used as a high-speed internet connection and port TV distribution in fiber to the home systems.